Okay, I'm just going to quickly work through the group work for this week. So we have mono substituted, so that looks like one R group, so R would represent any carbon. That's A. B is di-substituted, same carbon, so the hydrogens would both be on this carbon and the substitutions would both be on the other. C is tri-substituted, so that's going to give us 3 R groups and only 1 hydrogen. D is di-substituted, but the R groups are on the same side. E is di-substituted, but they're on opposite sides. So that's trans or E configuration. F is tetrasubstituted, so this is a completely substituted alkene, no hydrogens. And G is unsubstituted, so no R groups at all hydrogens. And so we're ranking them from most stable to least stable. So let's see, there's 1, 2, 3, 4, 5, 6, 7 of them. So no substitutions at all is going to be the least stable. So I'm going to give that 7. 4 substitutions is going to be the most stable. So I'm going to give that 1. And then next, tri-substituted. So that would be C. So far I have F is the most stable, followed by C, and then we're going to get into our di-substituted. So actually for di-substituted, we know that trans is better than cis, but if the R groups are on the same carbon, that's even better. So that would be B, I don't know why I put 3 there. That should be 2. And then 3. I think I put 3 because it has 3 substitutions. And then trans is better than cis, so then that would give us, let's see, E is the trans. That should be an R, but it doesn't look like it. Okay, so that's 1, 2, 3, 4. And then cis would be 5. So that's D. And then 6 would be just the mono substitution. That's A. 1, 2, 3, 4, 5, 6. And then very last is G, that has no substitutions at all. So more substituted is more stable. Okay, oh sorry, I was off the camera for part of that, but I think you guys probably followed okay. Okay, so now we're ranking the following alkenes from most to least stable. So again, more substituted is more stable. So I actually draw in my hydrogens just because I feel like that makes it easier to see which one's more stable. Like this is only mono substituted because there's 3 hydrogens left, and this is di-substituted because there's 2 hydrogens left. And then this is mono-substituted, and this is mono-substituted. So then we have to determine which one is EZ on this. And we can't use cis trans because there's 3 substitutions, not just 2. Okay, so we already know this is going to be the least stable because it only has, 1 substitution. This is going to be the next to least, and then 1 and 2 is between these. So I'm going to go ahead and assign my priority. I know that carbon is a higher priority than hydrogen. Now these are both carbons. This carbon is attached to a carbon and 2 hydrogens, while this carbon is only attached to 3 hydrogens. So this is higher priority than this. So the highest priority is on the same side. So same side, Z, same. I always think same, Z. It's kind of like S, so instead of same, it's same. I don't know. I just made that up, but that's how I always remembered. So this would be Z. So they're same side, so that's more similar to cis. So that's less stable than the trans version, which I believe this is, but we'll make sure. So this is higher priority, and then we already decided this is higher priority. So these are opposite. So opposite and E are both vowels, so that's how I remember that one. And E is more similar to trans. So this is going to be more stable, and then this one. So our order of stability is 1, 2, 3, and then 4. Okay, give the Iupac name for each of the following indicating E and Z. All right, so this is using all of the nomenclature you learned from 4 plus E and Z here. So let's see, 1, 2, 3, 4, 5. I think that would be the longest carbon chain. But I'm going to start my numbering from this side because it's closer to the alkene and there's a lower number of substituents. So it kind of both ways make that pentane. And then once I've identified my parent chain, then I start to find my substituents. So it's 1-chloro. It's also 2-chloro, so that'd be 1,2-dichloro once we write it out. 2-ene, and it looks like that's the only substituents. Now we have to determine if this is E or Z, because it's not going to be cis or trans because there's 3 substitutions. So carbon is a higher priority than hydrogen, but chlorine is a higher priority than carbon because chlorine weighs more. So we're only looking at just like with RNS configuration, the weight of the atom directly attached. So carbon to chlorine versus carbon to hydrogen. So this has the higher priorities on opposite sides of the double bond. If you cover it up, you have priority in 1 and 2 together on each of these, 1 and 2, instead of both ones. So that's E because they're opposite. So I would say E 1, 2 dichloropent 2-ene, or you could say 2-pentene. That would also be correct. Okay, similar 1, 2, 3, 4, 5, 6, 7. 7, so heptane is our parent chain. I'm going to start from this side to make sure that the alcohol and the double bond have a lowest possible number. So heptane. And then to identify our substituents, we have 2-ol, 4-ene, 5-methyl. Okay, so that would be 5-methyl, hept, 4-ene, 2-ol. And we put the ene before the ol because alcohols are higher priority than double bonds. So the highest priority comes at the absolute last when it comes to suffixes. But we still have to decide E or Z. So if I'm comparing these two, these are both carbons. The directly attached is both carbons. This carbon is attached to 3 hydrogens, while this is attached to 1 carbon and 2 hydrogens. So this is the higher priority. And then this is the higher priority because carbon is higher priority than hydrogen. So now you can see the ones are on the same side if you cover up the double bond. So if it's on the same side, then it's Z. So this would be Z, 5-methyl, hept, 4-ene, 2-ol. Okay, and if we go to C, so now let's go to C. Let's find the parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9. Nonane. And I actually think the side I started numbering it from is going to be right because that makes the double bond lower. We have a 3-methyl. We also have a 3-ene and a 5-methyl. So we're going to go ahead and combine all these together. We have 3, 5 dimethyl non-3-ene. You can also say 3-nonene. Either of those is correct. And then we have to identify E or Z. So this is going to be, we're looking at these 2 carbons. This carbon is attached to 3 hydrogens, while this is attached to another carbon and 2 hydrogens. So this is the higher priority side. And then this has an implied hydrogen here, so this carbon is going to be higher priority. So these are on the same side, so I'm going to call this Z, 3,5-dimethyl-nonene. Z for Zame. Okay, and then this actually looks like the exact same molecule, but instead of Z, it's the E version. But let's just count and make sure. 4, 5, 6, 7, 8, 9. So that's nonane with 3,5-dimethyl and the double bond right there. So yes, at the 3 position, I'm going to say, let's make sure it's E instead of Z. It's not just a trick of the eye. Sometimes I think I know and I get tricked. So this carbon has 3 hydrogens and this has a carbon and 2 hydrogens. So this is higher priority. And then this is higher priority because carbon is higher than hydrogen. So see how we have 1 and 2 on the same side of the double bond if you cover it up. So that's how we know it's E for opposite antigen. So this would just be E, 3, 5 dimethyl non-3-ene, or you can say 3-nonene, whichever. All right, for each of the following, draw the Zaitsev and Hoffman product. Okay, well, I accidentally paused my recording, and I don't know when that happened, so I'm going to just show you guys the answer to this one. I can't go back and watch the video without stopping the recording. I'd have to make it 2 separate videos. So I'm just going to show you that I solved this one. It was the exact same as this one. And hopefully you guys saw that. And if not, I'll just make another video. We'll see what happens. But I had just finished explaining how I identify the difference between Zaitsev and Hofmann product. So Zaitsev, it starts with an S. It's more stable, more substituted, and it comes from a smaller nucleophile. While Hofmann is bulkier, it's less substituted. The Hofmann product is a bulkier nucleophile, gives you the less substituted. So in this case, the nucleophile would come in and abstract that proton and form a double bond, and then the leaving group would leave. And while on this side, the nucleophile will take this proton, form a double bond, and the leaving group would leave. So if you have the bulkier, it'll go the black route. If you have the narrower, it'll go the blue route. So the narrower goes the blue route and gives you the Zaitsev product, which is also spelled like this. That's how I remember all these start with S. And the bulkier gives you the Hofmann product. So I'm just going to do that for each of them. This is the hydrogen where the carbon where the leaving group is attached. So you could either take this hydrogen or this hydrogen. Both of these methyl groups are identical. They would give you the same product, so it doesn't matter which one. This would give you the double bond would form here. Your nucleophile, your base would take this, form this, and your leaving group would leave. And then you'd have 2 methyl groups there. Or if you go the other route, the nucleophile would come and take this, would go there, and your leaving group would leave. So if you followed that route, you would get this product. Okay? And now for this one, we could take from this hydrogen, or either of these would be identical, so it doesn't matter. So I'm just going to pick one. This is going to be more internal. It's easier. It's less easy to get to, so you're going to use your narrow nucleophile to get the Zaitsev product there. And you'd have your methyl group where you after your leaving group leaves. Or with your bulky base, like tert butoxide, it'll come in here, and then your leaving group would leave, and you'd end up with something that looks like this. Just a double bond on the outside. Okay. Sorry about the confusion with my recording stopping there. I don't know how that happened, but hopefully at least you guys can follow to some degree what I was working on. Okay, to determine if Hofmann or Zaitsev would be favored, predict the products. So this is narrow nucleophile. So I'm going to predict that Zaitsev would be favored because it's smaller. So that means it's going to be the more substituted. But actually, if you look, these are the 2 options for the hydrogen that can be abstracted. So there's not a Hofmann or a Zaitsev product. They're the same either way. So either way, the nucleophile would come and attack. A double bond would be formed, and the leaving group would leave. And so either way, you're going to get a bond right here between carbon 2 or 3. If it took from the other side, it would be on this side, and you just start numbering from there. So it's actually the same. So it's neither Hofmann nor Zaitsev. There's only one possible product. But here, let's look. You can take from this, or actually, I don't think you could take from here because there's not a hydrogen. So again, there's only one possible product. So I may do bad questions, but that's okay. I think you get the point that this would be big and bulky, so it would favor the Hofmann product. So this would favor Hofmann, this would favor Zaitsev. Actually, in both of these cases, though, there's only one product. So if you want a more challenging question that has 2 products, we can just make this look like this. And then you'd have 2 options. You could take from here or here. And this would be taken because you have a bulky nucleophile. And you'd end up with this product. There you go. All right, let's move on to question 6. Okay, so this I think is a little bit more challenging, but this is about the idea that for Newman projections, the leaving group and the leaving group and the hydrogen have to be opposite to one another. They need to be anti-coplanar, so they need to be in the same plane but facing opposite. So when we learned our Newman projections, that would mean the leaving group and the hydrogen that's being abstracted need to be opposite each other. And when that happens, this is where the double bond is going to form. So this line is basically the double bond. These two groups, A and B, need to be on the same side, and then C and D will need to be on the same side. And that's how, if you have the possibility for E or Z conformation, you know which one it's going to form. Sometimes it doesn't matter because the groups are the same, but it's worth it to practice this. So here we go. Let's draw this Newman projection. I'm going to start, I always like to look from this direction. So that means if this is the plane of the page, the wedge is going into the plane of the page. So my wedge will be on the left. Nope, I meant dash is going into the plane of the page. So the dash will be on the left, and the wedge is coming out of the page. So if you look at it like this, it would be on my right, where my dash would be on the left. So dash on the left, wedge on the right, and then right here, your whatever's in the plane of the page is going straight down. And then from the back, we have what is in the plane of the page going up. We have our chlorine is coming out of the page, so it would be on the right. And then there should be an implied hydrogen right here going into the plane of the page. So in this case, your chlorine is lined up against a methyl group, which isn't really helpful because you need it to line up with the hydrogen on an opposite carbon that's going to leave. So actually, I would rotate this front carbon to give you a Newman projection where you have the hydrogen here, this methyl group has gone down, and this ethyl group is on this side. So your chlorine and your hydrogen are going to be what leaves. So that is basically where your double bond forms. And your methyl and your ethyl are going to be on the same side. And then your hydrogen and your CH3 are going to be on the same side. Okay, so do you see that? This is right where the double bond forms. It's almost as if the double bond is forming right here between these two leaving. So you have your ethyl and your methyl and your hydrogen and your CH3. Okay, now let's do the same thing here for our Newman projection. If I look from this angle, the dash is going to be on the left because it's going into the plane of the page. So that would mean it's on the left. And the wedge of the implied hydrogen is coming towards us. And then we have CH2, CH3. And then if we look on the back carbon, there's a chlorine going into the plane of the page, CH2, CH3 coming out, and a hydrogen that's implied on the wedge coming out of the page. Okay, so with that, our chlorine and our hydrogen nicely are already opposite each other, so we don't have to rotate anything. So we have a methyl and an ethyl. Oh, that's it. That's an isopropyl. I drew that wrong. So sorry. There you go. A isopropyl and an ethyl on the same side, and then an ethyl and a hydrogen on the same side on the bottom. And a quick way to check yourself is if you didn't lose a hydrogen, you might have accidentally drawn your Newman projection wrong or forgotten to put the chlorine across from the hydrogen, because you're always going to end up with one less hydrogen than you started. Okay. Next one for this Newman projection, let's see if we were looking at it from this angle. Oh, if we're looking at it from that angle, our bromine is coming towards us, so if we flip that, then it's going to be on the right. And there's an implied hydrogen going into the page as a dash, and then a methyl group coming straight down. On the back, there's an ethyl group coming straight up. And then this dash is going into the plane of the page, so that would be on our left if we turn to look at it as a methyl group, and then a hydrogen is on the wedge coming out. So in this case, again, the bromine's not opposite a hydrogen, so we want to rotate that back carbon. So we'll end up with bromine here, hydrogen here, CH3 here, leave that the same, and then the hydrogen has moved over. This methyl group is now pointing up, and the ethyl group is back here. So now we can draw our double bond forms with a methyl and a hydrogen on one side, and the CH3 and the ethyl on the other side. And I strongly encourage you to make sure that you're practicing drawing these on your own, because I often make the mistake of trying to figure out which, is it this hydrogen and the CH3 are on the same side? Or, I kind of get mixed up. So I really encourage you to make sure that you're practicing drawing these on your own as well. Okay, and then last but not least, we have our bromine, a hydrogen going into the page, and a CH3 coming down. And then on the back carbon, an ethyl, a CH3 coming out, and a hydrogen going into the plane of the page. Nice. This bromine and this hydrogen are already opposite of each other, so we'll have a hydrogen and the ethyl group on one side and two methyl groups on the other. So that would be our final product. Okay, now for this number 7, what is the product of the following reaction? We have our bromine and our hydrogen here are anti-coplanar the way they need to be. They're coaxial but opposite, anti-coaxial or anti-periplanar. This hydrogen here is not. So you can't get an elimination product between these two. It can only happen right here where the nucleophile will take this hydrogen, the double bond would form, and the leaving group would leave. So, and I always draw the products for these in the hexagon notation. I think that's just easier to visualize. This is a bad hexagon, sorry. But if this is our deuterium over on this side, the double bond would form between the deuterium and where the bromine used to be, and then the CH3 would be here. All right. Okay, I have about 9 minutes to get through all of these, so I'm going to tell you why I think each one is SN1, SN2, E1, or E2, and then we can go back through and do some of the products if I have time. But if I stop this video, I have to put up a whole different one. It's very annoying, so I'm just going to try as fast as I can. Okay, so whenever I'm trying to determine if it's SN2 or SN1, I look at the nucleophile, and if the nucleophile is strong, which generally is negative, it's going to favor 2. And if it's weak, which generally means it's neutral, it's going to favor 1. And then once you've decided if it's an SN2 reaction, E2 reaction, SN1, E1, then you narrow it down between elimination and substitution. So if it's primary, it's usually the substrate leaving group is primary, is usually going to favor SN2. If there's a narrow nucleophile, it's usually going to favor SN2. And if it's a tertiary leaving group, it's going to favor E2. And if it's a bulky nucleophile, it's usually going to favor E2 because it's big and bulky. It's not going to have a very good time getting in and substituting. If this doesn't, also heat favors E2. If this doesn't answer it for you, if there's a secondary carbon, and that's kind of trickier, you can consider the acidity, but I don't think we're going to need to do that for any of these actually. And then we'll go over to the 1 side. So E1 and SN1 are much harder, in my opinion, to tell apart because they have the same first step. So they're both favored by secondary and tertiary because the first step is the rate determining step is the leaving group leaving. So you need a secondary or tertiary to find a good carbocation. Heat and bulky nucleophiles still favor E1, whereas more narrow and no heat is going to favor SN1, but you might still get some E1 in that situation. So this is always how I tell, is I do this decision tree. So in this case, we have a negative nucleophile, so it's not neutral. It's basically negative OET. So I know that's going to be on the 2 side. It's a pretty narrow nucleophile, and it's a primary. So I'm going to say primary substrate leaving group. So I'm going to say this is SN2. And then for the next one, we have a weak nucleophile. It's actually H2SO4, so it's actually an acid. It's not even really wanting to attack initially. And actually, the first step in this type of reaction is going to be a protonation. But so it's weak, we know, so that puts it on the 1 side, and there's heat. So that's going to bring it over to E1 for me. H2O as the nucleophile, this is weak. So that's going to bring it over to 1. There's no heat, but it's also not especially bulky. So I'm going to say this is going to favor SN1, although some E1 might also take place. Br minus, this is negative, so it's a stronger nucleophile. And there's a primary substrate, and no heat, so I'm going to say this is going to be SN2. Terp butoxide is strong, so that's going to be, again, on the 2 side. It's primary, so you'd think, oh wait, no, that's not primary, sorry. I don't know, I was looking at that one. It is tertiary, so that brings it over to the elimination side, and this is a very bulky nucleophile, so I'm going to say this is going to be E2. This is NaH, so that's basically H minus. So H minus is negative, so that's strong. So it's going to go to the 2 side. It's a strong nucleophile. And once you've gone to that side, if it's tertiary, it's going to favor elimination more. There's not heat, so there maybe would be substitution, but I just can't really picture substitution happening on a tertiary that's this crowded with this secondary over here. So I'm going to go ahead and say that this would favor E2 based on the fact that this is a tertiary. SH minus, that's strong, and this is primary, so I'm going to say this will be SN2. And then NaSMe, so SMe, that's basically like ethoxide, only instead of OMe, it's S. So different, just a different nucleophile, but very similar. So not especially bulky, but this is strong, so it's going to go to the 2 side. It's a primary, and it's not super bulky, so I'm going to say this is still going to go to SN2. Although this quaternary group over here could hinder it some, there might be more E2 than normal, it's still primarily going to give SN2. Okay, so on this ethoxide, this is going to come in and attack and kick this out all in one step to give our final product on this, the OET, or you can draw it out like O-ethyl if you want. This E1 reaction is a little bit more complicated. I'm going to rewrite this H2SO4 as HA because it's easier for me to visualize. This is going to come over here and get protonated, so your first step is actually going to be your OH2 plus. And now that's a good leaving group. So your first step is actually an acid-base reaction. Then we start an E1 reaction where the leaving group leaves. Oops, I accidentally drew a hexagon. It's a 5-membered ring. And you get your carbocation. Now, a hydrogen being abstracted from either of these signs is identical, so it doesn't matter. But the A minus that's lost its proton is going to take that, going to fill this in, and you'll end up with a double bond. For this SN1 reaction, the first step is still the leaving group leaving. And, let's see, we have one, well, I drew that badly, but basically you have 2 methyl groups, so after your leaving group leaves, 1, 2, 3, yeah, I drew that kind of crazy, but then your water is going to come in and attack, so you'll end up with an OH2 plus, and then that would deprotonate, and so you'd get your OH. So that's your SN1. For the SN2, the Br would attack and kick out this leaving group, and you'd end up with just a swap out for a chlorine for bromine. For this tert butoxide, that is big and bulky, so it can lose a hydrogen from here, here, or here, but because it's big and bulky, it's actually going to be the Zaitsev product. Nope, the Hoffman product. So it's going to choose a hydrogen off this carbon, so it'll come in and take that hydrogen, form a double bond here, and this leave. It could also take from this one, those would be identical, but it would not choose this one because that would give the Zaitsev product, which would be more stable. So instead, you're going to end up with something like this. Or you can also draw like this. Either of these is identical. Okay, for this H minus, this one is narrow, so I think this E2 would actually favor the Zaitsev. So you could take from here or from here, either of those. And so I'm going to say it would probably take this one because that hydrogen is narrow, and you'd end up with a more substituted and more stable nucleophile that would look like, or a more stable substituted alkene that would look like this. Okay, this SH minus would come in and attack and kick out that I group, the leaving group, and you just end out with a swap of SH for the I. And then same thing here, SN2, come in, kick out, all in one step, and you'd end up with the SME. These don't have stereochemistry, so you don't have to worry a ton about that. I hope that was helpful for you guys, and if you have any questions for me, please reach out via email.